Hello everyone, this is Chandana NM from Sri Venkateshwara College of Engineering. Today we are going to know about VLSI fabrication. First, introduction to VLSI fabrication. VLSI or Very Large Scale Integration is the process of creating integrated circuits with millions or billions of transistors packed onto a single semiconductor chip. Fabrication involves the intricate and precise manufacturing of these complex circuits using specialized equipment and techniques. Semiconductor materials and wafer preparation. Silicon wafer fabrication. High purity silicon is the fundamental building block of modern semiconductor devices. Wafers are sliced from silicon ingots and undergo extensive cleaning and polishing to create a pristine surface for device fabrication. Epitaxial deposition. Epitaxial growth involves depositing a thin single crystal silicon layer on the wafer surface, enabling precise control over material properties and device characteristics. Thermal oxidation. Thermally grown silicon dioxide forms a highly quality insulating layer on the wafer, crucial for fabrication transistors and integrated circuit components. Lithography techniques. Photolithography, the workhorse of VLSI fabrication. Photolithography uses light sensitivity resists to selectively expose and develop patterns on silicon wafers. Electron beam lithography, highly precise direct write technique that uses a focused electron beam to pattern features at the nanometer scale. Extreme electroviolet lithography, emerging technique that uses extremely short wavelength light to achieve smaller feature size and higher resolutions. Nanometer imprint lithography, a cost-effective method that relies on mechanical deformation of resist to create nanoscale patterns. Thin film deposition. Thin film deposition is a critical process in VLSI fabrication where materials such as metals, insulators, and semiconductors are deposited in thin layer onto a semiconductor wafer. This allows for a creation of complex integrated circuits with integrate patterns and features. Common thin film deposition techniques include physical vapor deposition, chemical vapor deposition, and atomic layer deposition. Each method offers unique advantages in terms of deposition rate, film quality, and conformability. Ion implantation. Ion implantation is a critical step in VLSI fabrication where high energy charged particles are accelerated and driven into a semiconductor wafer. This precisely controlled doping process allows for the introduction of impurities to create the desired electric properties in specific regions of the devices. The depth and the concentration of the implanted ions can be carefully tailored to optimize device performance, enabling the creation of ultra-shallow junction, high-dose source, drain regions, and other advanced device structures. Oxidation and diffusion. Oxidation is the process of growing a thin layer of silicon dioxide on the surface of silicon wafer. This insulating layer is crucial for many semiconductor devices. Diffusion. Diffusion is the controlled introduction of impurities into the semiconductor material to create desired electrical properties. It's a key step in the fabrication of transistor and integrated circuits. Thermal budget. Managing the thermal budget, the total thermal energy input during the processing is critical to ensure desired dopant profiles and material properties in the final device. Metallization and interconnects. Metallization is the process of decompositing and patterning thin metal films to create the interconnections between different components on a VLSI chip. Commonly used metals include aluminum, copper, and tungsten. The interconnect structure, composed of multiple metal layers separated by insulating dielectric layers, allows signals and power to be routed across the entire chip. Careful design of the interconnect architecture is crucial for high-performance, low-power VLSI circuits. Packaging and assembly. Chip bonding. The integrated circuit chip is precisely placed and bonded onto the package substrate using advanced techniques like wire bonding or flip chip bonding. Encapsulation. The chip is encapsulated in a protective package often made of ceramic or plastic to shield it from environmental factors and physical damage. Interconnections. Electric connections are established between the chip and the package pins or leads to using fine wires or conductive traces enabling signal and power transfer. Challenges and future trends in VLSI fabrication. Miniaturization limits. As transistor size continue to shrink, physical limitations such as quantum effects and heat dissipation pose significant challenges to further miniaturization in VLSI fabrication. Process complexity. The number of steps and precision required in modern VLSI fabrication has increased dramatically, making the manufacture process more complex and costly. Emerging materials. Researchers are exploring the use of new materials like graphene, carbon nanotubes, and 2D materials to overcome the limitation of traditional silicon-based devices. 3D integration. Stacking multiple devices layer vertically is a promising approach to increase transistor density and performance without further miniaturizations. Thank you.